Thank you to Jan and the Fetzer Fund for having this fantastic morning session here. And I'm going to continue with the theme, well expressed by Hugh Price here. I'm going to talk some very big picture stuff, and then at the end I want to get down in the weeds and answer Tim's question, well, what might this look like in an actual model, to try to give you something to hang your hat on instead of inventing straw man versions of what these retrocausal models might look like. Now, we're here at a centennial, so I took that as a reason to start with 100 years of hindsight. And you can imagine all of us in the room time traveling back to 1917 and trying to explain to everyone where they've gone amiss and what needs to be redone, what part of their foundations that they've built all of this fantastic classical physics on needs to be scrapped. And we might all probably give different answers. Some people might say, well, all of this tower of foundations that we've built everything on, all the way up to general relativity, which has just been introduced, all has to be scrapped. And some people, I call anti-realists, and Copenhagen-ish viewpoints, things maybe aren't even there if you're not looking, might even say you're even wrong that there are even beables at the bottom of all this. And as Tim Maudlin well put last night, that's arguably not even physics, but there's still plenty of people who would take that viewpoint and say, we got to scrap this whole notion of reality. Now here, I think many of us, most of us, are committed that there's some kind of ontology going on. So maybe we don't have to drill down that far into the foundations, but a lot of people are in the camp of quantum realists. Definitely the Everettians, maybe with Lev accepted, say very clearly, yes, our ontology is the wave function. That's the beables, and it lives in this giant dimensional configuration space. So what we have to throw out is space-time. And really any viewpoint that takes the wave function as ontic is committed to this at some point. Now, Bohm made this huge step forward, and he said, okay, let's add some beables to space-time. Let's add the particles. But on top of it, you still have the wave function steering these particles around. And so some of the beables are still in configuration space. Even the two-state vector formalism, if you just take the standard wave function and double it, you're still stuck in configuration space for multiple particles. Now, the 1917 people might complain about this. They say, well, we like space-time. We don't want to give it up, and certainly many people in this room like space-time. And we'll talk about space-time in a little bit, but there's another category of people who do think maybe we can fit everything back in space-time, but I call them the non-localists, the people that okay, we have to explain the Bell inequalities via influences outside the light cone, and so we can keep everything in space-time, but what we have to throw out is Lorentz covariance. We have to have a preferred reference frame, we have to have spooky influences, what Schrödinger called magic. Now, the people in 1917 might be a little confused by the fact that we can't agree on exactly where to draw the line here, but they would be particularly bothered, I think, by the idea that we still don't have a way to get space-time back. If we go all the way to the quantum realist viewpoint and throw out space-time, we still don't have a good story of where space-time comes back in. Even this throwing out Lorentz covariance, they would ask us, oh, did it turn out that general relativity was wrong? And we would say, well, no. It's been 100 years, and we keep discovering that is right. We just gave a Nobel Prize for this amazing prediction of general relativity. And they would say, well, why is everyone so dead set on throwing out Lorentz covariance? Is anyone here? Is anyone just trying to fix this problem we already know about, that waves and particles are seemingly acting like each other and we're a little confused about in 1917 already? Is anyone working here? And I think it's a bit of a black eye that so few of us are trying to build a theory, a quantum theory, where all the beables are in space-time. We have the Lorentz covariance that we see. Why can't we maybe have a less deep excavation here, something that we can more easily connect to the rest of the physics we know? So that's where I'm going to be talking about. I'm going to be talking about, is there a class of paths forward that you do not have to excavate quite so deeply? I like space-time. Many of my best friends live in space-time. everything we've ever observed empirically is somewhere in some when. We have this fantastic theory of general relativity that doesn't play well with quantum theory. And very clearly, the reason why not is we're things in different domains. We have things in configuration space. We have things in space-time that don't play well together. If we had a model with all space-time localized beables, its unification is going to be easier. I think that's a trivial statement. Occam's razor comes into play here, just simply that you have a simpler and smaller domain of space-time than configuration space. But I'd like to say that even the non-space-time models, even the most committed Everettians, can't help but think in terms of space-time logic. There's all sorts of examples here, but one really nice one to think about is go back to quantum statistics, go back to Einstein and Bose, and the original logic of why you count quantum statistics differently. If you have two particles that are identical, and you imagine swapping them, and they both live in space-time, and you swap them, you get exactly the same configuration, so you don't want to double count it. But if these particles are really living in different dimensions of configuration space, and you swap them, that's not the same state anymore, right? If you really think things are in higher dimensions and you swap two identical particles, you don't have the same state, and you should go back to classical statistics. And the mere fact that we then have these rules that essentially get to the same result without the good logic of having these particles live in the same space-time, I think is yet another piece of evidence that maybe this configuration space is not the way to go. And yet, it works so well, right? It's so successful in making predictions. What should we make of this fact? I mean, it's successful in statistical mechanics, too. Nobody takes it as literally the state of the particles in this room is in a 3n dimensional configuration space. So the mere fact it's successful shouldn't make us think it's real. And really, if you think about it, any limited knowledge framework of many particles, you want to be in configuration space to encode the correlations. Otherwise, you can't encode all these correlations in any limited knowledge situation. In StatMech, there's a real space-time configuration in classical StatMech of the particles. But if you want to encode the correlations, you need configuration space. So what is this configuration space wave function? It's got to be a state of knowledge, just like in StatMech. And there's lots of good arguments for this psi-epistemic viewpoint I could go into, but I'll just give you one. And that's, say there's something to the uncertainty principle. Say there is something we don't know. I don't find that too outrageous a statement, although many physicists say, oh, we know everything, we know the wave function. But let's say that's not right. Let's say there's something we don't know. If there's something we don't know, and we have a particle theory, how do we describe it? We know from StatMech we need configuration space. So you would be forced into a configuration space theory simply because we don't know something. Then you say, well, what happens when I learn new information? I update my state. You do Bayesian updating on your state. And you would expect to have a theory in configuration space that you update every time you make a measurement and learn something. And that's exactly what we have in quantum theory. That's just one of many, many arguments pointing toward this idea that the wave function isn't real, it's a state of knowledge. Of course, and we're all here at an emergent quantum mechanics meeting looking for something deeper. So even if you don't buy any of this, hopefully you admit that, okay, let's explore. Let's look around and see if we can find a deeper theory here. And that's exactly what I'm arguing. I'm arguing that what we have in quantum mechanics is apparent. It's just a state of knowledge about some underlying reality. There's something down here. That's the whole idea of emergence, right? That we have something from which quantum mechanics is going to emerge. What might that deeper explanation look like? We have a great clue. We have this whole branch of physics that tells you everything lives in space-time. It's very successful. Let's use it as a guide and look at restricted knowledge situations of that. So what's this deeper explanation going to be? It's not going to be quantum gravity, because we're not quantizing gravity. It's going to be the opposite. Right? It's going to be some story of quantum phenomena that lives in space-time. Not quantum gravity, but space-time quanta. So that's the big picture argument for why we should be looking at this. The easy answer for why nobody is looking at this is Bell's theorem. It's impossible. It can't be done. Don't bother. So That seems a little too glib. Let's zoom in here a tiny bit more. We see correlations between Alice and Bob that seem naturally explained by these hidden variables, by a common cause. Let's call it a common cause, lambda, some beables here. And the standard reading is you assume this independence assumption. You assume statistical independence. What does that mean? That means that whatever is down here, whatever these common causes are maybe we don't know them, or maybe we do, but they're independent of the future settings. That's statistical independence. The idea that there are some common cause here that's independent of what Alice chooses later and what Bob chooses later. From that assumption, if you keep everything in space-time, you kill Lorentz invariance. You say, well, there's got to be some influence. It's got to be maybe a faster than light. Well, it has to be faster than light because of the new experiments. It has to be unblockable, unobservable, a perfectly correlating influence that somehow can't be used to signal. That is the path forward. The other path forward is don't start with statistical independence. Start with Lorentz covariance. We have a lot of good reason to believe Lorentz covariance is accurate. And then what you do, as Hugh kind of argued, is that proves that statistical independence fails because Bell inequalities are violated. OK, what does that mean? That means that a common cause here, whatever lambda's down here, maybe we shouldn't call it a common cause anymore. We just call it beables down there that are sort of mediating this zigzag, have to be dependent on the future settings. That's the retrocausal story, that these variables somehow are constrained by the future settings. Now, as weird as that may seem, we have entire space-time at stake here. We have Lorentz covariance at stake. Let's spend 10 or 15 minutes considering it before we leap back into configuration space. Especially because I'm going to make the point that we don't even demand statistical independence of all of our other classical physical theories. If we're going to hang everything on it, it better be rock solid. And it's not too hard to come up with an example in classical that people take seriously that violates statistical independence. And what I have here are closed time-like curves. People consider these seriously. They're beables that depend on the future space-time geometry. I am not going toward this, by the way. I'm not going to say we need to explain entanglement with closed time-like curves. That's not where I'm headed. My point is that this is an example people seriously consider that violates statistical independence. Now, why? Why are they allowed to violate it and not us? The reason is that you can't get closed time-like curves from a Hamiltonian formulation to GR. You only get them when you solve Einstein's equations all at once, when this Lagrangian perspective. There's a different type of explanation that leads you down this path that gets you to a natural violation of statistical independence. And we have that same tool available to us. It's called action principles. It's called the Lagrangian schema. There are two ways we do physics. The first one we learned is the Newtonian schema. This was named by Lee Smolin. He called it this. Basically, you start with some state space. Could be configuration space, could be space-time, something. You have an initial state, and you have rules. And the universe solves it, so you can picture the universe as a big computer, right? Solving itself one time step at a time. This is what Matt Leifer was calling the standard ontological model framework. We're very comfortable in this framework. We think about it all the time. It's not the only explanatory schema we have available. We also have the Lagrangian schema. Instead of a state space, you look at a history space. You're looking at the full histories, the full trajectories. Instead of an initial state, you have initial and final constraints. Or in classical field theory, you have a full closed hypersurface boundary constraint. And then, instead of dynamical rules, you have some global rules. Some global, you extremize the action, or you do something else to the action. You use the path integral. And you solve it all at once. You're not solving the universe as one time step at a time. You're solving it all at once. In general, when you do this, you don't have statistical independence. Now, exhibit A of that is closed time-like curves. But exhibit B is simply that the final boundary here, if there's any way you can control that, then that's a setting. Think of that as a setting. And the global rules then, the history that is in here is going to be constrained by that. In a laser cavity, your setting of one near the cavity constrains the normal modes inside the cavity. This is kind of like a four-dimensional cavity problem. if you want to think about it that way, solved all at once. Yes, if your global rule is extremize the action, you can almost always drop back to the Newtonian schema, where we're comfortable. But if your global rule is something else, like path integral, it's not obvious you can do that, or something else that nobody's thought of yet. There are plenty of global rules here where you get clear violations of statistical independence without having any Newtonian schema fallback. That's what I'm interested in. There's really nice reasons to think about path integrals and Lagrangian schemas. Here's a cartoon of path integral account of a particle going from one point to another versus, say, a collapse interpretation. There's a lot of nice things here. You got your symmetries. I mean, this is why people use it in GR. This is why people use it in particle physics, right? You don't use a Newtonian schema. You use the Lagrangian of all the particles. You get all your gauge symmetries. Here you get your time symmetry for free. This on the right doesn't look very time symmetric at all, does it? The Bohmian account looks better on that front. The histories that are the history space is a four-dimensional space of histories. You don't need to foliate it, right? You could foliate it. You can foliate it any way you want, but you don't have to. You can just solve it all at once. But the key point I want to focus on is the final boundary constraint. That is what's going to give us our way to build models. Without a final boundary constraint, we're at sea here. We don't know how to build the models. But we do if we take it literally. A lot of people don't take that final constraint literally. They see it's a mathematical trick just to get back to the Newtonian schema. But you have to impose it to get it to work. Let's consider a few minutes taking it seriously as a literal boundary constraint, maybe on the subsystem or on the whole universe, if we're thinking cosmology. And maybe what these principles are telling us is that we've been too limited. We like the Newtonian schema. It feels intuitive to us. But it's limiting. And let's take a peek outside for a few minutes, see what's out there. OK. You may not see the connection between the final boundary constraint and violation of statistical independence. So here's one more argument that will hopefully make it clear. From time symmetry. If you accept that basically measurements and preparations are essentially time reverses of each other, you can get the point I'm trying to make here. Now, we have agents involved with measurements and preparations. Agents we have our thermodynamic arrow. We have differences between the way we perceive the past and the future. And so there are asymmetries here. It's not a perfect symmetry. But all the asymmetries are coming in through the agents, not through the physics. And we take it as uncontroversial that if we prepare a particle with a big laboratory apparatus, that the future beables, whatever flies out of our apparatus, is constrained by our setting, our preparation. That's pretty uncontroversial. It comes out in an eigenstate. It seems natural to us that that would be the case. And big things constrain small things, right? We have lots of examples in classical physics of big things that are acting as boundary conditions on smaller things. So this seems normal to us. Time symmetry, people say they like it. But if you really apply time symmetry to this case, that means if measurements the time reverse of some big cameras measuring a photon, just apply that same logic in reverse, you now have a final boundary condition on those very same beables that are coming in. If you can do this, we're done. Bell's theorem is not a concern. We violate statistical independence because the past beables are constrained by our free choice of setting, which is the whole assumption, right? That lambda in the past can't possibly be associated with what Bob chooses and what Alice chooses. In this story, they are. It's constrained just like think of a four-dimensional cavity, right? Some boundary constraint in the future constraining the past. You can't change the past in the literal sense. Change involves time. Some event in the past is there. There's the block universe perspective. And so you do not want to think about things sloshing back and forth in time. You just want to analyze it all at once. I call this the all-at-once viewpoint. Sometimes the retrocausality is a nice word. It confuses people, I think. I've been moving to just all-at-once stories, which I think is maybe Tim likes it better anyway, right? OK. So my point before I get into the nitty-gritty here is that there's hope for space-time. We just need this Lagrangian schema viewpoint. You got to have future constraints, but I see it as a small technical price for recovering Lorentz covariance. Yes, it's technically retrocausal because your choices in the future control the boundaries. The boundaries constrain the past. Yes, it's retrocausal. But once you're back in space-time, so many problems get solved. Even the measurement problem loses its sting. You don't have this problem where, depending on the size of the system, you have a different size configuration space, and you get a different answer. It's all space-time, all the way down. OK, that's the big picture. Of course, Tim's question, the hue, well, what's going on? What's going on this zigzag? The straw man version of this, is I got 5 minutes till questions? 10 total. 10 total. OK. Here's the straw man version we got to kill, is things sloshing back and forth in time. When you start thinking about that, you're applying Newtonian schema logic, right? You're starting with a state and evolving it, sloshing from Alice to Bob through the past. That's nuts. It's like provably wrong, because your notion of time, in one sense, is having it slosh backward, but your notion in time has already been represented as a spatial axis on this diagram. So as soon as you start thinking about things sloshing back and forth in time, you're using 2 time dimensions without even realizing it, and you're not in space-time. So you got to think about this as a block. You got to think about it all at once. Things are not sloshing back and forth in time here. They are static things on that diagram we need to use to explain the correlations. What do we need? We got to solve it all at once. We ideally want time symmetry. That's just the whole motivation for a lot of this, as we saw. We got to obviously violate Bell inequalities, and we got to give Alice and Bob their freedom. Coming from outside the system, we're not modeling them. They're the boundary constraint. They got to do whatever they want. OK, so here's an example in the last couple minutes here. This starts with a one-particle model from Larry Shulman. You may know him from his Path Integral book. Basically, the model is just you have a spin 1/2 particle. It really is pointing somewhere. It's pointing here at this time. It's pointing at this angle. It's pointing, and then here at this time. And you impose the measurements, the pair of measurements, as boundary constraints. How does it get from here to here? Well, it's got to rotate. He has some rule for the probability of rotation of a net angle beta. We're going to set gamma to 0, and basically he comes up with this ansatz. Maybe this is the probability. Notice the probability is assigned to the whole history here. It says what's the probability of that history, not the probability of a state, the probability of a history. Now, what's the final boundary condition? Well, what do you choose? You choose the setting. I'm going to choose this axis to measure the spin. I can get the red outcome or the green outcome. That's my boundary constraint. It's forcing one of those 2 outcomes. So you have a bunch of possible rotations. You could rotate 0.4 pi to get to the red here, and you calculate the probability. You could rotate negative 0.6 pi to get to the green, or you could rotate around an extra 2 pi, an extra 4 pi. So he works out the sum here of all the ways to get to red, all the ways to get to green, and he gets the Born rule in the limit that gamma goes to 0. I mean, he still started with this assumption, but basically, this assumption leads you to the Born rule. So I thought this was cool. And of course, we have this great example from Hugh, how the 1-particle and 2-particle stories are the same. So I'm going to skip through all this and show you how the 2-particle works. All you do is put 2 of them together. Take 2 Shulman's particles, and you classically entangle them. What do I mean? You just say their spins are unknown but opposite. That's classical entanglement. So it's easy to do. It happens all the time with conservation of angular momentum. They're hidden. You don't know what they are. They could be pointing in any direction. But they're opposite. It's not enough to get Bell inequalities, obviously, with the Newtonian schema. But the key here is you don't assign a uniform probability distribution in all directions. That would be assigning probability to initial state. That's not what we do. We assign probability to the whole history. When we calculate with Shulman's approach the probability of this whole history all at once, we're looking at the probability of a net rotation alpha and a probability of a net rotation beta, and we just calculate the joint probability in the usual way. Now, when you do this, you go through the math, and it turns out it's overwhelmingly probable that all of the anomaly happens on one arm or the other. And here's the proof of that, but you can take my word for it that you work it out. What's the net probability of a partial rotation here and a partial rotation here? It turns out it's overwhelmingly probable that it all happens on one arm or the other. Now, that seems unlikely to you probably because you're thinking, well, that would mean that one side doesn't rotate at all. And what are the odds that the initial state is just happen to be aligned with this one of these future settings? But that's exactly what happens in these models. You solve it, and you discover it's overwhelmingly probable that the past hidden variable is correlated with the future setting. And this just comes out of the math here. This isn't like some weird thing that comes in. When you analyze these all once, this happens every time. You put a final boundary condition on a problem, and you get exactly the sort of retrocausation we need to explain this. And the punchline is that you get, in this case, the right probabilities. It doesn't just violate Bell's inequality in principle. It actually gives you the right probabilities. This is actually what we see. This is what you get from this model. It works for all possible measurements on all 2-qubit maximally entangled states. That's kind of the best model we have right now. I'm still working on extending this to partial entanglement, and we'll be continuing to work on that. If we can get the partial entanglement, I think the sky's the limit. So, I'm out of time. Don't give up on space and time. We like space and time. I think Emily Adlam is going to talk about going from states to histories. And the contrast I want you to keep in mind is the alternative. If the alternative is going to 3n dimensions, adding 1 dimension doesn't seem so bad. It's easy to violate statistical independence if you think in terms of the Lagrangian schema. We're still at the toy model stage. We might need hundreds of physicists to all pile on this to get to the next level. But it's new. Nobody's working on this. Maybe there's a grad student in here that's going to have one key insight. Say, you do this to the action, you solve for the histories, and maybe out will come something that looks like quantum mechanics. Thanks very much.